Our next speaker is Nathan Berkovits, and his title appears to be Hiroshi test. That's my introductory slide, as Jan told me kept it there. So it's tough to follow up Jan's jokes, but I'm gonna first of all, let me thank the organizers for inviting me, and of course thank Hiroshi for all of his involvement with my work. And of course, there are a few features I have in common with Hiroshi. So we both like topological strings. We both have a good friend with Qumran. We're both bipolar in the sense that he's east-west and I'm north-south. And we've both been sucked a little bit into administration. But there are also things that are very different. So I'm, of course, in awe of Hiroshi for many things. But I remember the first time he came to Brazil was about 15 years ago, and he was giving a lecture through a lecture series, about 100 students, and he was doing it all in real time on an iPad. And of course, now every high school student knows how to do this, but he was, giving the lecture in real time and changing colors and fonts. And it was the first time I'd ever seen anybody do this. And of course, everybody wanted to imitate him. But that was a huge success. And of course, also his ability to absorb and also summarize the results of other people. So that's a special attribute of Hiroshi, which I think everybody admires very much. So there's one paper I wrote with Hiroshi together with Qumran, and it's actually a little bit related to the topic I'm going to talk about today. In the sense that what I'm going to talk about today is a C hat equals 5 topological string, which turns out to be related in a way I'll describe with pure Spinor formalism. So of course, in the paper with Hiroshi, it was something very different, that he was working together with Qumran about this open-closed duality. But the C hat equals 5 theory hopefully is something that will be in common with other things also. Okay, so okay, there we go. Okay, so the title of my talk will be to relate this C hat equals 5 theory that I'll describe, which is called D equals 5 holomorphic Chern-Simons, with this pure Spinor formalism. So hopefully this will appear soon on the archive. So I'll start by reviewing 2 other formalisms for the superstring, RNS, which I think everybody knows, and this pure Spinor description, which was developed maybe 20 years ago. And there's still a mystery about how to relate these two. So as I will say, they both are very successful, but they describe slightly different aspects of the string, and everything that's been computed using both formalisms coincide, but one would like to understand better the relation. And it turns out RNS is described as an n equals 1 string theory, and pure Spinor is as n equals 2, or more precisely topological n equal 2. And there's another type of string theory which can be described as n equals 1 and n equals 2, which is this holomorphic Chern-Simons. And it turns out that the relation between the n equals 1 and n equals 2 description of holomorphic Chern-Simons is very similar to the relation between RNS and pure Spinor. So it turns out you need a slightly more extended version of RNS, which I'll call BRNS GSS. And by twisting this new kind of superstring in the same way as Chern-Simons can be understood as twisting the RNS, you can understand the pure Spinor formula. So one of the subtleties, which is still not understood, is that when you do multiloop amplitude computations in RNS and pure Spinor, they look very different. And there's subtleties in both, but even understanding how the subtleties are related is something that's not understood. And I think hopefully this work that I'll discuss today will be useful at understanding that. Okay, so just to review the superstring. So RNS, I think everybody knows very well. It has manifest n equals 1 worldsheet supersymmetry, but the spacetime supersymmetry is hidden. You can, of course, compute using very hard work, Dope and Fong. We're able to compute 2 4-point over Schwarz amplitudes, but it's very complicated because you need to sum over spin structures to get the explicit answers. And of course, Ramon vertex operators and Ramon backgrounds are complicated using RNS. Of course, there's the Green-Schwarz formalism, which has manifest spacetime supersymmetry, but in that formalism, covariant quantization is complicated. Now, if you go to lower dimensions and only require 4-dimensional, 6-dimensional manifest spacetime supersymmetry, there's a hybrid formalism, which I developed together with Qumran, and also that was discussed in my paper with Hiroshi. And but if you want to covariantly describe the 10-dimensional theory, you need to use this pure Spinor formalism, which, as I mentioned, has this twisted n equals 2 worldsheet supersymmetry. And as I mentioned, all computations that can be compared with RNS coincide, but people have gone further. So Marfra and another student of mine, Gomez, was able to compute 3-loop 4-point and also 2-loop 5-point together with Oliver Schlatter. So these are things beyond the RNS computation. And of course, spacetime supersymmetry is manifest in the answer, and there's no sum over spin structures. So it's a very simple formula, but we still don't know how to relate these computations with the RNS computation. Of course, we can also compute curved backgrounds Of course, there the life is more difficult because the background is it's not quadratic action, but you can do computations with manifest PSE24, and hopefully that will be a future application of the form. Okay, so just to review the pure Spinor formalism. So it involves the worldsheet variables of Green-Schwarz are called Green-Schwarz-Siegel because it includes also the conjugate momentum to theta. So it turns out if you want to describe Green-Schwarz formalism with first-class constraints, you need to introduce this conjugate momentum to theta. And in addition, there are variables which play the role of ghosts. So they turn out to be constrained variables, which is called the pure Spinor formalism. This is the d equals 10 pure Spinor constraint, as Cartan would call it. And in addition, it turns out useful to introduce these non-minimal variables, which don't appear in the vertex operator, but they're useful when you want to describe what I'll call the B ghost. And when you do computations, they decouple from the cohomology because they appear in the BRC operator in a simple way, and that's why they're called non-minimal. So as I mentioned, this formalism has an n equals 2 twisted worldsheet supersymmetry. So G plus would have conformal weight 1 and G minus would have conformal weight 2. And you can see that the stress tensor is quadratic. So this is, of course, in a flat background. So these are just three fermions in the conjugate momentum. So theta, lambda, and lambda bar and r would have conformal weight 0, and the conjugate would have conformal weight 1. And G plus is built out to this, well, in Green-Schwarz language would be the constraint. So this d alpha is built out to the conjugate momentum. So it's like dd theta plus theta ddx if you think in terms of superspace. And this is the non-minimal term, which tells you that the vertex operator, the physical states, will be independent of the non-minimal variable. Now, G minus, which is the conformal weight 2 generator, is more complicated, and it plays the role of the B ghost. So in topological string theory, G minus plays the role of the B ghost. And as you can see, it involves this supersymmetric version of X, and also it has these inverse powers of lambda, lambda bar, which will turn out to cause some complications when we discuss multiloop amplitude. And then you have this ghost, which you can think of as twisting the theory. And this, of course, this is the U1 generator. Okay, so as I mentioned, to define physical states, you need to construct the BRC operator of G plus, so it has the simple form. And the unintegrated vertex operator, so just for the massless open string, is just described by the Spinor gauge superfield of super Yang-Mills. And this is the integrated vertex operator. So it involves not only the Spinor gauge superfield, it also involves the vector gauge superfield of Yang-Mills. And this would be the field strength whose lowest component is the gluino, and the field strength whose lowest component is the gluon field strength. So it's not so complicated, and you can use it to compute. So this would be amplitude prescription. So as I mentioned, G minus plays the role of the B ghost, so it's sewed in with the Beltrami differentials as you would do in bosonic string theory. And then you have the vertex operators, and it turns out many of these worldsheet variables have zero mode. In order, when you do the computation, you get lots of zeros over zeros, just because some of them are bosons and some of them are fermions. It's topological in the sense that all of the fields have conformal weight 0 or 1, and you have cancellation between the number of bosons and fermions, but you still have to regularize, and that's what this regulator comes in. And now the question that you want to answer is, how is this topological n equals 2 amplitude prescription related to the usual n equals 1 RNS prescription? And in this talk, I'll explain how this holomorphic Chern-Simons gives a clue to how to relate these two prescriptions. Okay, so what is d equals 5 holomorphic Chern-Simons? Is a complicated name, but okay. It's essentially a generalization of the d equals 3 Chern-Simons theory, but it's holomorphic, so it's like the 2B model. So you can think of it as 10-dimensional super Yang-Mills compacted to 5 complex dimensions. But it turns out physical states, instead of being just the general dimensional super Yang-Mills states compactified to 5 complex dimensions, they have to be in the cohomology of one of the spacetime supersymmetry generators. So if we break the SO10 down to U5 times U1, then we just choose one of the generators to carry the U1 charge 5/2. And then we look at the cohomology. So the subset of states of super Yang-Mills, which are in that cohomology. And it's easy to see because in the supersymmetry algebra, this Q plus has a commutator which gives you just 5 of the momentum. So we also split the vector up into a 5 and 5 bar. It turns out just to describe super Yang-Mills states which have PA with the lower index being 0. So you can conveniently combine all of these super Yang-Mills fields into this superfield here. So it's a scalar superfield which has 5 anti-commuting parameters. So it has 2 to the 5th. It has the same number of degrees of freedom as super Yang-Mills, but you have to remember that all of the fields only depend on 5 complex X's. So the Xi's would be the gluinos, and the A would be the gluon, and you can see one of the gluinos appears in some, if you like, it's like the integral of Xi. So the 3-point amplitude is actually very simple to write down. It's just the product of these 3 and integrate over the 5 gammas, and you get the 3-point D equals 5 holomorphic Chern-Simons amplitude. And you can also use the topological theory to compute these amplitudes. So the n equals 2 string, which describes the theory, is just given, it's essentially the same as the D equals 3 Chern-Simons, but now you have 5 gammas instead of 3. So it turns out you can either use the usual RNS formalism, where you restrict the external states to be super Yang-Mills states, depending on only 5 of the 10 X's, or you can compute using the topological framework. So how are these related? So I'm not mentioning references in this paper, I mean, in this talk, but this was first studied by people, at least from my knowledge, people like Nekrasov and Beaulieu, and of course, Kevin Castell has written recent papers on it. So the idea is you want to twist the n equals 1 into the n equals 2, so you have to define what the U1 generator is. And the convenient way to do that is to split the psi's into complex psi's. So we call gamma and gamma bar just splitting the 5 psi's, the 10 psi's into 5 complex pairs. And we change the conformal way to do the twisting by either multiplying by gamma or gamma to the -1. So if you bosonize or fermionize the beta gamma system like Friedan, Martinek, Schenker, using the C8 and 5 fields, then gamma to the -1 would just be C e to the -5. Now, when you do that, of course, the BRST operator has a simple form in the sense that, for example, gamma G just splits up into one without a gamma and one with a gamma, but now gamma will always appear squared. So we define gamma tilde to be gamma squared. And if we fermionize gamma tilde, we find a very simple relation. We find that eta tilde, which would be the eta ghost associated with gamma tilde, turns out to be just equal to the space-time supersymmetry generator in the -1/2 picture. So this Q plus condition, that Q plus annihilates the equals 5 holomorphic Chern-Simons states, can now be just understood as a requirement that states, these holomorphic Chern-Simons states have to be in what's called the small Hilbert space. They have to be annihilated not just by eta, but also by eta tilde. So that's the way you define this subsector of the superstring. Okay, finally, of course, this is the RNS generator, but you can relate it to the usual n equals 2 BRST operator by doing a similarity transformation, which essentially just removes all the terms from here, G plus and gamma tilde B. And now you can recognize that the cohomology of this operator is just the cohomology of the holomorphic Chern-Simons plus the requirement that it's independent of these extra ghosts, BC and beta tilde gamma tilde. So after you do that, and if you put the RNS picture changing operators on top of the B ghosts, then you find that you just reproduce the usual n equals 2 topological prescription. So that's the way to relate these two, at least for holomorphic Chern-Simons, and it's not completely trivial, but it's straightforward. So now we want to reproduce this for the pure spinor, so we have to start with the n equals 1 string theory. Now we want to start with the n equals 1 string theory, which has both worldsheet supersymmetry and spacetime supersymmetry. And we can do that by adding some fields, which you can think of as RNS non-minimal field. So we're going to introduce a pair of fields, theta and lambda. So you can think of this as an n equals 1 worldsheet superfield, and this is their conjugate momentum. And of course, these thetas will play the same role as in the Green-Schwarz-Seeger formula. And then we're also going to do some non-minimal variables, which will be related to the non-minimal pure spinor variables. So we have the RNS string, and then we add this new n equals 1 superfield, which has, you can see it has 32 bosons and 32 fermions. And similarly, it is non-minimal in such a way that the conformal weight contribution from these cancel the conformal weight contribution from these. So we still have a critical n equals 1 superstring, but we have these extra fields. Now, the nice feature about adding these extra fields is that after performing this similarity transformation, so the similarity transformation here, the n equals 1 generators now become manifestly space-time supersymmetric. So these p's and thetas combine now into the Green-Schwarz-Seeger variables, what you call d alpha and pi, in such a way that the n equals 1 worldsheet theory is supersymmetric. The BRST operator is, of course, just a standard n equals 1 BRST operator, but now with these as the generators. And you can construct the Yang-Mills vertex. So it turns out to have this simple form where these A alpha, AM, and W alpha are the same super Yang-Mills superfield as before. So part of it looks like the RNS vertex operator for the gluon, this term here, but you need all the other terms in order for it to be BRST invariant. So it's kind of like a mix of the RNS and the pure Spinor formula. It's straightforward to compute scattering amplitudes, at least 3 amplitudes using this. There's no longer any spin fields. All the fermions are now described by these fields depending on theta and P. And it's easy to show that it agrees with both the pure Spinor and RNS computations. But of course, this is one of the vertex operators, but of course, because you have these extra fields, you need some other restriction in order to say that these vertex operators are the only physical ones. And to do that, we're going to use the intuition we got from holomorphic Chern-Simons. We need this extra condition analogous to eta tilde. So this extra condition, we have to figure out how to twist. So we have to build a U1 generator, which has the property that if you commute it with G, so this G here, it's going to split it into a G plus and G minus, which forms an N equals 2 algebra. It's not so straightforward to do, but it turns out J has this form. So it depends on these extra non-minimal variables. So it just takes half of them to be twist to be conformal weight 1 and half to be conformal weight 0, but also twist the psi. So the psi start out as being spin 1/2, of course. And this term here splits half of them to be 5 of them to be conformal weight 0 and half to be conformal weight 1. Just like in the D equals 5 holomorphic Chern-Simons. But of course, lambda is now not a fixed direction. So lambda and lambda bar are these pure Spinor variables. And it turns out you need another term in J in order for this J to split into G plus and G minus. So what are these lambdas and lambda bars? So originally we started with this capital lambda, which was just an unconstrained spinor. So it was not a pure spin. And lambda bar similarly. And now we're going to extract pure spinors from them with these definitions. So of course, this capital lambda has 16 components, which is described by these 11 components of the pure spinor and this UM. So UM is essentially a vector with also some constraints. So this is a bit complicated, and because of this complication, you also need this extra term in J, but you can now do the same trick as before. So you twist all these gammas with the gamma, and capital gammas with the small gamma and small inverse gamma, so that now capital gamma has conformal weight 0 and capital gamma bar has conformal weight 1. And we also twist the non-minimal variables so that all of them come conformal weight 0 and 1. And similarly, we define gamma tilde to be equal to gamma squared and beta tilde to have the property that is conjugate to gamma tilde. And from that, we can extract what eta tilde was as before. So it always has this simple form where J is the derivative of H. But of course, because J is more complicated, it has these terms here. So the idea now is that if you take this BRNS GSS string, so of course combines features of the pure Spinor and RNS and Green-Schwarz-Siegel formalism, and you split the N equals 1 generator into an N equals 2 generator in this way, and that defines what you mean by this special subset of states, then the claim is that this subset of states annihilated by eta tilde describes precisely the superstring states. So those are the amplitudes which are supposed to agree with the amplitudes computed the RNS forms. Okay, so how do we work with that? So as I mentioned now, the physical superstring states should be annihilated not just by the BRST operator and by the eta ghost, so they have to be in the small normal Hilbert space. They all should be in the small tilde Hilbert space. So again, we can write now in terms of the twisted variables. So now G plus appears without any gammas and G minus appears. So this is exactly the same as in the D equals 5 holomorphic Chern-Simons. And again, we can do the similarity transformation as we did for the D equals 5 holomorphic Chern-Simons. So that the BRST operator essentially just built out of G plus, but now you have all these extra variables. So of course, the original pure spinor was just lambda alpha D alpha plus W bar R. But now we have these extra non-minimal variables, which essentially tell you that the physical states will be independent of these extra non-minimal variables. And G minus, thank you. And G minus is related to this complicated expression for the B ghost that I wrote down 2 transparencies ago. So here's the B ghost was here. And it turns out that if you set gamma bar to be 0, which is of course one of the restrictions coming from the homology. Sorry. So gamma bar is of course one of the constraints. So it turns out G minus is just the pure spinor goes plus terms which depend on gamma bar. And you just plug into the n equals 2 topological amplitude prescription. Then you recover something which looks like the pure spinor amplitude prescription. So of course, the super Yang-Mills vertex operator, which I wrote down before, should be related to the pure spinor version of the vertex operator. It turns out that there are extra terms coming from the non-minimal variables, which are more complicated, but at least this is equivalent to this in the cohomology sense. And now you should be able to try to use the same prescription as you use for Holomorphic Chern-Simons, or for n equals 2, to compute the prescription. But as I mentioned, there are certain subtleties in the pure spinor multiloop amplitude prescription which are not present in the INS. And of course, they're also not present in Holomorphic Chern-Simons. So let me now finish by discussing some of these subtleties. So in the pure spinor formalism, of course, one has the B ghost, but one has dependence on these non-minimal on these inverse powers of lambda lambda bar. So it turns out that if you ignore these problems, then there's a subtlety in the BRST cohomology. It turns out that if you have enough powers of these 1 over lambda lambda bar, everything that is BRST closed is everything that's BRST closed is BRST exact. So the cohomology becomes trivial. So you have to be careful when you say that something is BRST trivial, that something that's BRST trivial can be ignored if it has inverse powers of lambda lambda bar. And that's essentially the problem that comes in if you try to do higher loop computations using the pure spinor formalism. Now, there's a nice feature about the pure spinor formalism, which is not true about RNS, and the picture changing operators have no singularities with each other. So that's, of course, also true in the Holomorphic Chern-Simons, and it's just because the picture changing operators are built out of G minus, and G minus has no OPEs with G minus, whereas, of course, G, the n equals 1 generator, does have OPEs with itself. So there's a mystery about how this is, how can this be explained if the amplitude is supposed to be equivalent? And what I'm now going to try to explain is how this relation with n equals 2, with Holomorphic Chern-Simons may explain it. So it turns out that when you relate the n equals 1 picture changing operators to the n equals 2 picture changing operators, and also when you relate the n equals 1 vertex operator to the n equals 2, you have to do a similarity transformation which has this form. So it's built out to eta, which is the untwisted, from the untwisted beta gamma ghost, and xi tilde from the twisted gamma tilde. So it has this form. Now, one thing you can see is this capital A is in the small Hilbert space of the tilde theory, of the untilde theory. Okay. It's in the, what do I want to say? So what I want to say something. So it turns out this capital A takes you from the n equals 1 vertex operator to the n equals 2 vertex operator, but it takes the n equals 1 xi ghost into xi plus xi tilde. So when you do the similarity transformation, it doesn't take the n equals 1 picture changing operator into the n equals 2 picture changing operator. So n equals 2 picture changing operator will be q of xi tilde. The n equals 1 picture changing operator is q of xi. So it turns out that what happens when you do this transformation, it takes q xi into q of xi plus q of xi tilde. And it turns out q of xi, of course, has OPs with itself. So it's just the original n equals 1 picture changing operator. But in the tilde Hilbert space, you can ignore it because it's BRST trivial. So that's because xi, although you can write it in terms of the tilde variables, it doesn't depend on xi tilde. So it turns out to commute with eta tilde. So this is in the small tilde Hilbert space, which means q of xi is BRST trivial in the small tilde Hilbert space, in the small tilde Hilbert space. So in this term here, you can ignore it. At least in the Holomorphic Chern-Simons computation, you can ignore it because it's something BRST trivial. But it turns out when you do the computation in the pure spinor version, this H turns out to involve 1 over lambda lambda bars. Remember that J had these terms with inverse powers of lambda lambda bar. So xi, when you write it in terms of the tilde variables, has these inverse powers. It means you cannot ignore them. So that's a subtlety or a complication, which means that when you have terms which involve these inverse powers of lambda lambda bar, they may accumulate in such a way that you can't ignore this q of xi. Now, there are certain terms in the pure spinor amplitude computations where these lambda lambda bar poles never accumulate. They turn out to be for computations of supersymmetric F terms. In other words, terms when you compute in d equals 10, they preserve at least one of the d equals 10 spacetime supersymmetry. So at least for these supersymmetric F terms, the RNS and pure spinor computations precisely coincide. For the D terms, terms which do not preserve any of d equals 10 supersymmetries, you have to, at least in the paper written with Nikita Nekrasov, you have to do some complicated regulator. And it's much more complicated to compute. So up to now, multi-loop amplitude terms have only been computed for F terms using the pure Spinor formalism. And I believe that this Q of psi is going to help to compute these D terms in the sense that we're going to have to carefully understand how they enter into the D term computations. And that's essentially going to explain how to relate these multi-loop subtleties in the two formulas. Thank you. So just to summarize, so the relation, so what I showed here is that the relation between RNS and D equals 5 holomorphic Chern-Simons. So this, of course, you can compute as an n equals 1 theory. This is an n equals 2 topological theory, is equivalent to the relation of this BRNS GSS, this n equals 1 worldsheet supersymmetric and spacetime supersymmetric version of the superstring with this n equals 2 version. Now, twisting requires constructing this J, which implies that you have this eta tilde, which can be explicitly written in terms of J, where J is the derivative of H. And physical states have to be, if you want them to describe the superstring states, have to be annihilated by all of them, which implies, as I mentioned, that when you do the transformation from n equals 1 to n equals 2, you have to include the contribution of this Q of psi in the picture changing operators if you're going to analyze D terms in this pure Spinor form. Okay, so of course, hopefully this will be useful for understanding better the relation. And so let me just finish by again thanking UOC and congratulating him on his birthday.
Yeah, so I just have a very basic. So D equals 5. So what's so special about D equals 5 in this case? Or are you just using this for convenience to understand the n-dimensional operation?
So of course, if you start with RNS and you twist, then you get a C hat equals 5. So we want the theory before twisting to be just a critical n equals 1 string. So
is this because you use complex structure in all of these calculations?
Well, if you want, you can work with 5 plus 5. So you can work in signature SO55.
Okay.
And then all the things can be real. So I'm not so worried about the analytic continuation. I'm just saying that if I start with the RNS and I twist it, I'm going to get a C hat equals 5. So of course, I also always want to start with the C hat with the C equals 15 n equals 1 theory. So that forced me to discuss the C hat equals 5 for the n equals 2 theory.
Any other questions or comments? I don't see any hands. In that case, I think we have a coffee break.